Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the last lecture of module 1. In today's lecture, we are going to discuss about equation of motion, and then we will be discussing about elastodynamic wave equation that will be used to find out P and S wave motion. The concept that we are going to cover today are equation of motion, P and S wave motion, and before we delve into today's lecture, we will summarize the previous lecture, what we have learnt in the previous lecture. As far as the summary of the previous lecture goes, we basically talked about the stress tensor sigma ij or ji, and it has basically the 9 component, and this is the traction T1, T2 and T3, and in the expanded form on plane 1, plane 2 and plane 3 it looks something like this. And if we talk about Cauchy's stress theorem, the traction vector Ti is basically a function of unit normal vector on which the force is being applied, and it is the dot product of stress and the normal unit vector. And the strain tensor is given by EKL, that is half of del UK by del XL plus del UL by del XK. Now the constitutive relationship that we talked about in the previous lecture was for the elastic isotropic medium. It is in the form of Hooke's law. It looks something like this, and when we consider the various symmetries and isotropy of the medium, then all the elastic moduli of CIJKL basically reduce to 2 moduli, that are Lami's constant, lambda and mu. And in terms of Lami's constant, the stress tensor looks something like this, and this del operator is Kronecker delta function, and the relationship can be expressed as in terms of lambda and mu separately. We can write something like this. This particular term is related to the compression, and this basically is related to the shear, and this compression is also related to the normal stresses. That's why you can see there is a theta term, which is a dilatation term, and this dilatation looks something like this, that is theta is equal to E11 plus E22 plus E33. That means it is the trace of the strain tensor. Now if we start with the lecture today, then before we even go into deep of the today's lecture, let's learn something starting from the very basic. What are the scalar field, what are vector field, what are the divergence, what are the gradient, and what are the curl. So scalar field, every point in space is assigned a scalar value. That means it doesn't have any direction, but it does have the position, and it is denoted by phi x, or in terms of position it can be phi x1, x2 and x3. And vector field has both values and the direction, and it can be written as u x1, x2 and x3 because it is a vector field, so it will be in bold letter. And if we expand it in terms of in the direction of x1, x2 and x3, which has the unit normal vector E1 cap, E2 cap and E3 cap, then it can be U1, x1, x2, x3, E1 cap, U2, x1, x2, x3, E2 cap, plus U3, x1, x2, x3, E3 cap. So when we are looking at the spatial variation of the scalar vector or the tensor field, then there is an operator that we are going to deal with, is the del operator. It is something similar to inverted triangle, and in all 3 direction it is E1 cap del by del x1, E2 cap del by del x2, E3 cap del by del x3. And the first thing that we are going to talk is the gradient. The gradient is a vector field formed from a spatial derivative of a scalar field. I repeat, it is the spatial derivative of a scalar field. So, spatial derivative of the scalar field means it is the spatial derivative of phi x. So, that means if phi x is the scalar function of the position, the gradient is defined by something like this, grad phi x, or inverted triangle or del phi x, and it can be written something like this, and these are all the partial derivatives. And the divergence basically describes the spatial variation of a vector field ux, and it is given by the scalar product of del operator, or you can say the dot product of the del operator with ux or vector field. And this is it can be written in this form: divergence of u is equal to del dot u, and when we take the dot product, the vector field will change into the scalar quantity. Then it will be del u1 by del x1, del u2 by del x2, and del u3 by del x3. And the divergence basically used to measure the net flow of the fluid from a given point. That means if the divergence at a point is positive, it implies that point is a source. That means if there is a source, then the field will be going out from it. And if it is negative, then it is basically a sink, and if this is a source, then the field will be coming towards it. That means it will be a sink. Now let's talk about the curl. The curl operator is basically applied to the vector field, and it yields another vector field, and this is your curl del cross u, and when we take the cross product, then it looks something like this. And in the determinant form, you can do the curl with the vector field, something using this matrix form, where the top row is E1 cap, E2 cap, E3 cap. This is your del operator, and this is your vector field. And there are these two identities that someone must remember, because these identities are going to be used in today's lecture to basically find the solution of the elastodynamic wave equation. And these identities says that the divergence of a curl is 0 and the curl of a gradient is 0. So basically, when the divergence of a curl is 0, it represents no volume change, and if there is no volume change, then it may give rise to the shear waves. If the curl of a gradient is 0, that means no curl or rotation, and it may give rise to the compressional waves. And this is another identity that we must remember, or you can say what is Laplacian, and Laplacian is basically the divergence of the gradient of a scalar field, and it is represented by del square. And when we take the del square of the scalar field, that means the divergence of the gradient of the scalar field, that it may look something like this: del square phi by del x1 square plus del square phi by del x2 square plus del square phi by del x3 square. The Laplacian of a scalar field produces another scalar field, and an important identity for the Laplacian is looks something like this, and this identity will also be used in the solution for elastodynamic wave equation. So let's start with the equation of motion. And equation of motion, as I can tell you, it basically relates the stress with the ground motion. So basically you want to relate your stress with the ground motion during the happening of the strain. So basically you can say all the ground motion that are happening on the ground is basically from the stress. So you want to have some kind of equation that can relate stress to the ground. So basically the spatial variation of the stress field are related to the ground motion, and that is further related to the strain. So basically according to this equation, the acceleration, or you can say acceleration, is basically the double derivative of the ground motion or the displacement field. So according to this equation, the acceleration results from the body forces and the surface forces. So basically, when you are writing this equation, these are your stress field, and this is your body forces. So you can see these are basically the surface forces, and these are basically your body force, and that is basically equal to rho del square u by del t square. If we are writing the equation of motion in one particular direction, and in this case in the x2 direction, then it may look something like this. So basically this particular term that you are seeing here, this is your spatial variation of the stress field, and that spatial variation of the stress field is basically due to the force. So you can see this is a important information in that the spatial variation of the stress fields gives rise to the force, and there it can be added to the body force term, and finally it may be equal to the rho into del square u by del t square. So in the x2 direction, this equation may look something like this. So the note that is provided here is the equation of motion relate stress tensor to the ground motion or displacement. And in summation convention, it can be written something like this: del sigma ij x comma t by del xj plus fi x comma t is equal to rho del square u xt by del t square. And in this equation, this sigma ij can also be written as sigma ji, because you know the stress is a symmetric tensor. So this particular equation can be written in this form as well. So it is interesting to know that the divergence of the stress tensor, or you can say the spatial variation of the stress tensor, or you may say the divergence of the stress tensor, give rise to the force, which is a vector. So this is basically very interesting, because the divergence of the stress is a tensor quantity. So when you take the divergence of stress tensor, it is basically giving you the force. So force is a vector quantity, and when you take the divergence of a vector, then it can give you the scalar. So it is written, it is interesting to note that the divergence of the stress tensor gives rise to a force which is a vector, just as the divergence of a vector yields a scalar. So if the body is in the equilibrium, what will happen? The acceleration will be 0, because in the equilibrium, body will either be traveling at a constant speed or velocity. That means there will be no acceleration. So in that case, the del square u by del t square will become 0. U will be remain with only a term, that is del sigma ij x comma t by del x is equal to minus fi x comma t. So this particular equation is known as the equation of equilibrium. Now let's talk about if there is no body force. Okay, if there is no body force, that means you are talking about the homogeneous equation of motion. So in the homogeneous equation of motion, that means you are lacking some forces. That means we are already saying there are no body force, there is some lack of forces. So in homogeneous equation of motion, when we apply, there is the fi x comma t will become 0. So in that case, the equation of motion will become something like this, and that will be known as homogeneous equation of motion. And this homogeneous equation of motion, because if we are not talking about the forces at the source location, or we are not talking about explosion, this equation describes the seismic wave propagation. That means except at the source, such as the earthquake or an explosion where body force generates seismic waves. Now, we will use this equation of motion to basically derive the expression or the differential equation for P and S waves. So what we have seen here, the equation of motion can be written and solved entirely in terms of displacement, because stress is related to strain, which is formed from the derivative of the displacement. And the equation of motion basically relates the spatial derivative of the stress tensor to the time derivative of the displacement vector. So this displacement vector is what? It is nothing but it is the ground motion. So basically we are relating the stress with the ground motion. So the ground motion that you see in the case of an earthquake, this basically generated from the stress that is applied on the earth. So the equation of motion in the x direction may look something like this, which is we have seen in the case of equation of motion. And since we are considering a homogeneous medium, so the above equation do not poses any source term. So you can see there is no force term, body force term is missing here. So because we are considering the homogeneous body medium, and in the homogeneous medium there is no source term. So now the stress tensor in the previous lecture we have seen can be related to the Lami's constant, lambda and mu, and there is this Kronecker delta function. If we expand it into the x direction, you can say if we want to write the stress onto the phase that is normal to the x component, then there will be three components: sigma xx, sigma xy, and sigma xz. So we are going to derive the elastodynamic wave equation first for the x direction, then we will expand it to the y direction, and then we will also going to be expand it into the z direction. Then finally we will write a summation term to basically describe a single equation describing the stress in all the direction. So now this is for x direction, and in the x direction sigma xx will be something like this, and sigma xy will be like this, and sigma xz will be something like this. So how it has been written, sigma xx, that means I and j both are equal to x. So that means if they both are equal to x, that means the delta ij will become 1, and the term that will remain is lambda theta, and this is 2 mu, I is equal to x and j is equal to x, so that means 2 mu e xx, so that is lambda theta plus 2 mu, and e xx can be written from the equation that we have seen, e k l is equal to half del uk by del xl plus del ul by del xk. So that means when both are equal, then these terms will become equal to each other, and finally what you will get, half of del u x by del x, right? So if you look at the formula that we have just shown you, here is the formula. So what we have seen in this formula, so EKL is equal to half del UK by del XL plus del UL by del XK. When we are saying both terms are x, that means you are talking about that this term del UX by del X plus del UX by del X, so that will basically turn it into this particular term. Right, so that is what we have written here, and this will be del ux by del x. So now if we talk about sigma xy, then the Kronecker delta x delta function will become 0. Only term that you will be left with this one, and this will lead to mu exy you can expand using this particular formula, and then you can get this. Likewise you can do the similar thing for this. Now since we are talking about the spatial derivative of the stress tensor, then you can take the spatial derivative of the sigma xx, sigma xy and sigma xz. So when you take that, and then it may become something like this. Now when you are summing all the spatial derivative of the stress tensor in the x direction, then it may look something like this, and that when you will sum them up, then on the right hand side you will get something like this. And then when you will collect all the terms, lambda plus mu, so del square ux, and another term lambda del square ux by del x square, this one, then it may become something like this. And then you will collect mu terms, and all these mu terms, when you will sum them up, it may represent something like this, and lambda mu plus mu, this will something like this. So you just need to rearrange this one to this one, and now when you will take another rearrangement, and this particular thing can be written something like this, and then you can write, you can basically collect mu separately, and it may become something like this. Now when you will talk about this equation in x component, so it may for x component, so basically what they are doing here, this basically is what? It is nothing but your dilatation term, that is your theta, and this particularly is your Laplacian. So this, when you will do this for the x component, then this will be lambda plus mu del theta by del x plus mu, this is your Laplacian x direction, rho del square ux by del t square. Likewise for the y component of the equation of motion, the similar thing can be written. For the z component also it can be written like this. Now these three equations can be combined to get something like this, where del square u, this del square u, basically your del square ux, del square uy, del square uz. Now we need to find out, using this particular identity, the particular equation, we need to find out where are the p and s waves, and for this purpose we are going to use this particular identity. Now we can separate this particular term using this identity. So the previous equation, if you use that identity, will become something like this. So there will be this term that you need to solve, and there will be this term that you need to solve separately. Then what we are going to do, we will assume that this is your m and this is your n, and we will then solve it separately. And to solve this particular equation even in a more simpler manner, because we want to relate the displacement field with their respective scalar and the vector potential, and for that purpose we are going to use Helmholtz decomposition. So as per the Helmholtz decomposition, it says that any displacement field can be decomposed into its scalar and the vector potential. Here the vector potential is your epsilon xt, and here is your vector potential, scalar potential is your phi xt. Now we are going to use the other two quantities that we just saw when we began this lecture. That is your curl of the gradient of scalar field is 0, and that is your divergence of the curl of the vector field is 0. So when you use these identity and take m and n separately, so this is your m and this is your n. So this u can be decomposed into its scalar and the vector potential. So when we are doing so, when we are writing it like this, del phi x comma t plus curl of epsilon x comma t, this is your vector potential. So this scalar potential basically is responsible for p wave, and this vector potential is basically responsible for s wave. So when we do so, then you can basically get del of del square phi plus del cross curl of x comma t. So this will become del of del square phi x comma t, because this will become 0, because it is your divergence of the curl of a vector quantity. Likewise, when we use this, then this n and here u can be replaced with the Helmholtz decomposition in the form of scalar and the vector potential. Then it may become something like this, and this quantity when you will solve, it will be something like this. Now when we incorporate all this thing into your previous equation, then your previous equation may look something like this. This is your lambda plus 2 mu del square phi xt minus mu del square del this is your curl of the epsilon or vector field, that is equal to rho del square by del t square, and that is your gradient of scalar plus curl of the vector quantity. Now when you will rearrange this equation may become something like this. So to solve this equation, what we'll have to do, you will have to keep this term separately as 0 and this term separately as 0, then only you can find the solution of this equation. When you do so, when you do this as equal to 0, what it will become? It will become lambda plus 2 mu del square phi x comma t minus rho del square phi x comma t by del t square. When you will keep this as 0, then your mu del square epsilon x comma t minus rho del square epsilon x comma t by del t square will become 0. When you take this as 0, this becomes something like this, and here alpha, this is your del square phi x comma t, that means del square, this is your scalar field. So because it has a scalar field in it, so it is basically related to your compression, and or you can say it is related to your p waves, and this alpha is basically nothing but your p wave velocity. So p wave velocity we are going to represent as alpha. So this alpha is basically nothing but it is equal to under root of lambda plus 2 mu by rho. Likewise, for S waves, it will be del square epsilon x comma t, because it is a vector potential, so it will be representing your S wave 1 by beta square del square epsilon x comma t by del t square, and this beta is equal to under root mu by rho, where mu is the shear modulus or modulus of rigidity. Now if I will say this is your p wave equation as we have derived in the previous slide, the scalar potential satisfying the above equation, for finding solution that may basically solve this equation, we can consider this phi xt as this thing. That means if the wave is traveling in z direction, positive z direction, then your phi z comma t may look something like this. So that is phi z comma t a exponential iota omega t minus kz. The wave is traveling in positive z direction. So if you want to find the displacement of the particle of this wave along which it is traveling, you just have to take the gradient of the scalar field. So gradient of the scalar field phi z t you can take, and when you take the gradient of this particular term, then this gradient will become something like this. So if you remember, how did we take the gradient? For taking the gradient, if you remember, we saw that this is the gradient, del phi x by del x1, del phi x by del x2, del phi x by del x3. So since the wave is traveling in z direction, so the first two terms will become 0 and the last term will only be remaining with minus iota k. So when you will solve it, so this term, then you will remain with s, so, and then finally a exponential iota omega t minus kz. The displacement of the particle is along the direction of the propagation of the wave. So that means in p wave, the particle motion is along the direction of the propagation of the wave. So the dilatation term, that means because we are talking about the compressional wave or the p wave, that means dilatation term will be non-zero. That means because in compression what happens? The volume changes. So that means during the dilatation the volume will change, and that means the dilatation will become non-zero. So to see that, when you will take the divergence of the displacement field, then it will be non-zero. Okay, so that means there is a volume change. Likewise, you can say as the wave propagates, the displacements in the direction of propagation cause material to be alternatively compressed and expanded. Thus, the P wave generated by scalar potential is called a compressional wave. Likewise, for S wave, you can describe the vector potential. So the vector potential for S wave can be described something like this: ax, ay, az exponential iota omega t minus kz. To find the displacement of the shear wave, the particle along with the shear wave is traveling. To find the displacement, you can take the curl of the vector field of the shear wave, and when you take that, it may become something like that. And only the component along the x direction and y direction will remain, and the component along the z direction will become 0. That means the particle motion is in the perpendicular direction to the propagation of the S wave. Now you can say the P wave causes change in the volume and S wave causes no change in the volume. Now that was about last lecture of module 1. So as far as the revision of module 1 goes, we can just see that what we have done in the lecture 1. In the lecture 1 of module 1, we have used the force balance to derive the 1D wave equation. We did an overview of parameters that describes harmonic waves such as lambda or the wavelength, period, frequency. We have also talked about the wave number. We derived reflection and the transmission coefficient. If you remember, we derived R12 and T12, and this R12 was ρ1 V1 minus ρ2 V2 by ρ1 V1 plus ρ2 V2. Likewise, T12 was 2 ρ1 V1 by ρ1 V1 plus ρ2 V2. Likewise, we looked at kinetic energy and the potential energy averaged over a wavelength, and we found the kinetic and the potential energy was both equal to half a square omega square rho. And an alternative method of solving a differential equation is through normal modes. And stress describes the force per unit area, and it is a tensor quantity. It is a 3/3 tensor quantity. And the traction vector is the surface force per unit area on a plane with given normal. And in the engineering, so Sate and Stein book uses the engineering convention, so in which the tension is positive, and that is why stress in the earth is going to be negative. And stress tensor we saw has the following qualities, or you can say following properties. Stress is a symmetric tensor. It can be rotated into any other coordinate system, and coordinate system without the shear stresses give rise to principal stresses, and these are basically known as the eigenvalues of the stress tensor, and trace of the stress tensor is independent of the coordinate system used. So this is basically the invariance of the stress tensor, and the pressure we can relate to the trace, that is basically the mean of the trace of the stress tensor. Likewise, the deviatoric stress we defined, deviatoric stress tensor is the stress tensor minus the pressure. And when we talk about the unit of stress, that is Newton per meter square or the pascals. And in the earth situation, we talk about the pressure. That means if we increase the depth by 33 kilometer, then the pressure will increase roughly by 1 gigapascal. And we also talked about the elastic moduli tensor or the stiffness tensor, that was represented by CIJKL, and that basically describes the behavior of an elastic material. And the Lami's constant lambda does not have any physical meaning, but mu is called the rigidity or the shear modulus. A material with large mu is quite rigid and responds to a given stress with less strain and vice versa. A material in which the shear modulus is 0 cannot support the shear stresses and corresponds to a perfect fluid. And we also saw that the stress can be represented in the matrix form. It has 9 components, and the traction is basically can be related to the Cauchy's stress theorem, which is a function of the unit normal vector on the surface on the forces where the force is applied, and its direction is similar to the force. And the strain tensor is given by EKL half of delta UK by del XL plus delta UL by del XK. Now we have also talked about the Hooke's law, and Hooke's law relates the stress with strain, and it is for the very small order of the strain, that may be of the order of 10 to the power minus 11. That means sigma ij is equal to CIJKL EKL, and in the expanded form, in the form of Lami's constant, it can be written something like this. And the relationship can be expressed in terms of Lami's constant in the form of compression and the shear, or in the form of normal and the shear stresses. It can be written something like this, where theta is the dilatation term and the delta is the Kronecker delta function, lambda and mu are the Lami's constant. And theta, this dilatation term, can be written as the trace of the strain tensor, and that is some of the normal strains on the matrix. Now, the equation motion that we discussed today relates the spatial variation of the stress field plus the body wave term, that is equal to the rho and the acceleration of the body. And the elastodynamic by wave equation that we talked about looked something like this. So that was the end of module 1. In the next module, we are going to discuss about Snell's law, and also we will be discussing about the reflection and the transmission. So that was all for module 1. So these are the references that we have cited for the material that we have used today, and thank you so much. Bye-bye.